Dear everyone, I am Professor Tang, one of the lecturers responsible for the course Fluid Mechanics and Thermal Fluids. Now this video is made for the laboratory P02B. Now in this video, I will give you a brief introduction on the theory and reason for carrying out the laboratories, and then your lab tutor will give you a demonstrations. Now let's get started.
The title of experiment P02B is the investigation of the factors that affect the friction loss in pipework. The aim of this experiment is to study what are the factors that affect the frictional loss in SWEG pipes, and then we also introduce a method to calculate the roughness of the internal surface of pipe. So why it is so important to carry out these experiments? Now, I think you will know that pipes are actually very important components in buildings. Now, for example, you can find pipes or ducts in the HVAC system. You can find pipes in the sprinkler systems, and also water supply and disposal system consists of pipe works. Okay, now what are the factors that we are going to study in these experiments? Now, because the fluids, no matter water or air, has viscosity, so there will be a frictional force acting on the internal pipe surface when water is moving inside the pipe, right? Or air is moving inside the duct. Now, these frictions, therefore, will result in static pressure drop, that is, the flow will lose its energy, and this loss has to be compensated by pumps and fans, otherwise the flow will not be moving in the desired flow velocity. Now, so the question is, how are we going to predict this friction so that we can select the right fan and pumps? Now, in these experiments, we look at how this friction is related to the internal surface roughness and the diameter of a pipe. Now, the experiments will be carried out, of course, in the lab. The test rig we are using is the Edicton hydraulic test rig. Now, this is a very comprehensive test rig. In our experiments, now we focus ourselves on SWEG pipe, right? So there are altogether 5 SWEG pipes section in this test rig. Now you can see why pipe section number 2 is a rough pipe. The diameter is 17 millimeter, and we have other rough pipe which has a larger diameter, and we have smooth pipe, very small diameter, and we have 2 other smooth pipe in the experiments. Now, please be reminded that for smooth pipe doesn't mean that the friction is 0. Okay, for smooth pipe, it still have friction. Now we will be handling this in the lecture later on. Now, in these experiments, we will be using pipe these 2, 3, 4, 5, and 6. So what to measure and what to estimate? Now, in these experiments, we are going to measure we are going to study the pressure drop due to the friction inside the pipe. Now, we will be using the data to calculate the roughness of each pipe, which are not given, right? Okay, now what to measure? On the test rig, there is a flow meter that we can measure, which we can use to measure Q, the flow weight, and then we are given the diameter of each pipe, so the flow velocity can be calculated by dividing Q by the cross-section area of the pipe. Right, we can also measure pressure drop across the pipe section, right, and then the pressure head loss is given by this formula, This is the density of water, which can be assumed to be constant, and then G is the acceleration due to gravity, which is also a constant. Right, the friction factor is divided in this form. Right, F equal to the head loss divided by these numbers. Okay, now in the experiments, then we adjust the flow rate, vary the flow rates, and then we measure the pressure drop, and then calculate the frictional head loss. Right, now after a series of measurements, then we can plot this head loss against u squared divided by 2g, which is called the kinetic head of the flow. And if you plot this graph, then the slope is this, right? The slope is the friction factor times the length of the pipe, which is constant, divided by the diameter of the pipe. So once you have the plot, then you can just look at the straight lines, right? And find the slope, and then from the slope you calculate the friction factor. Or in some situations, someone will prefer to plot log head loss against the log velocity. In this case, this is an equation, and the y-intercept will give you the friction factor directly. Of course, there are many different ways to get F. So I think you just have to stick to a particular methods. Graphical methods is what we are expecting. Okay, now after we have the friction factor, then we go on to calculate the pipe roughness of each pipe. So once you have the friction factor, we can then find the relative roughness using a Moody chart, which is figure 3 in your left sheet. Now this Moody diagram relates friction factor with Reynolds number and relative roughness. Okay, so we have to calculate Reynolds number. Now Reynolds number is given by this formula. The Reynolds number RE equal to density of the water in this case, right? And the velocity, the flow velocity, the diameter of the pipe divided by the viscosity or coefficient viscosity of water. And you can find the coefficient of viscosity against from table 1 in your left sheet. Okay, so table 2 in the work sheet. Okay, so once you have F and Reynolds number, then we can actually plot this F and G on this Moody diagram. This is the Moody diagram, right? The Moody, you can now, if F here and then FG here, you can plot upon on this Moody chart. Okay, just like for example, here is the example. Right now we have suppose we calculate F, and then we have Reynolds number, then we have a point here. And now how to calculate the relative roughness? Now these lines, right? These lines are roughness, lines of constant relative roughness. So what you need to do is to interpolate the relative roughness by using these lines, right? And then once you do the interpolation, then you find relative roughness, and relative roughness is equal to the absolute roughness divided by the diameter of a pipe, and therefore you find the roughness of the pipe. The title of experiment P02C is Investigation of Dynamic Losses of Pipe Bands. Now in these experiments, we are going to study the factors that will affect the dynamic loss experienced by a fluid when it moves across a pipe bands like this. Now, as you all know, pipes are very important components in buildings. However, they are not usually straight because there are many occasions where a change of flow direction is required. Now, you can find pipes and bands in the HVAC systems, in the sprinkler systems, and also in the water supply and waste disposal systems. Now, when the flow changes directions, energy will be lost. And if you want the flow to maintain at this fixed flow rates, then this energy loss has to be compensated by pumps and fans. Now, the question is, how are we going to predict this loss so that we can select the right fan and pumps, and also how the bend angle affects the energy loss. Now, this is the major aims of these experiments. Okay, in these experiments again, we are using this hydraulic test rig on the screen. Right, and we are using two bands here. The first one, yes, is band number 16, and the other one is band number 19. Now, band number 16 is dual right angle band here, and band number 19 is a 40-degree angle band. In these experiments, P02C, we are trying to estimate the dynamic loss coefficient capital K of each band. Now, we are going to test the K value for 3 bands. The first one is the 90-degree band, single 90-degree band, and the other one is the double 90-degree bands, and then is band 19, which is 45-degree bands. And we are going to observe the effect of bend angle on the dynamic loss coefficient K. Okay, now what are we going to measure? Now we will be measuring the flow rate Q, right? The flow rate Q, and then we can calculate the flow velocity using this formula. The flow velocity is equal to Q divided by the cross-section area of the pipe. And we also measure the static pressure drop across the band, and by definition, the pressure drop across the band is equal to the dynamic loss coefficient K multiplied to the kinetic head of the flow. In the experiments, we vary the flow rate and measure the static pressure drop. Now, because we expect this static pressure drop is proportional to rho u squared divided by 2, therefore, if you plot this static pressure drop against rho u squared divided by 2, then the slope of the line should be the dynamic loss coefficient K. Okay, after finishing one band, then we repeat the above using other bands and observe the differences in K. Now let's go to the laboratory.
Hi everyone, this is the experiment test rig about experiment number P02B and number P02C. The experiment mainly investigates about the factors that affect the friction loss in pipework and the dynamic loss in pipe length. So we all know that from the fluid mechanics, if the fluid flows inside the tube, it will receive friction loss, and the friction loss is caused by the pipe, and also it has dynamic loss caused by blends. So the friction loss is generally associated with the length of the tube, the diameter of the tube, and the roughness of the tube. So in this test rig, we have 5 sets of tubes, which has different diameter and different roughness. The length of the tube are all treated as 1 meter. And for the dynamic loss in pipe blends and fittings, we are going to investigate 3 sets of bands. That is, these bands that contains 2 90-degree of turns, and this one with 1 90-degree turns, and this one with 135-degree turns. So the whole test rig contains these sets of pipes and blends, and a pump below this desk, a flow meter, a rotary flow meter that sends the flow rate to the computer on the right-hand side, which I will show later, and also these valves, and these are pressure transducers that can record the pressure signal. So for the measurement, we have a computer here, and the computer records the signal sent from the test rig. Basically, there are flow rate and the pressure. So the flow rate can be adjusted by this actuator here, and I don't know if it's clear here. But anyway, I'll give the results in the data sheet, and these are the value of the sensors. So to start the test rig, we first opens a valve, that is the valve on the first pipe, and connects the pressure transducer on the left and right hand side shown in this video. And we can start the test rig. And we can see from these two figures, this is the variation of flow rate and the pressure signal. So for about 1 or 2 minutes, and when all the data gets stabilized, we'll record the value of flow rate and these sensors and the pressure sensors. And once we have one set of data, we can adjust the flow rate by the actuator again to get another result. I think it's not very clear in this video, but I will give the value, all these data in the data sheet. So that's all. Thanks for listening.